We're now going to take an entirely different approach to the problem of finding similar sets of items without looking at all pairs of sets. These methods are suitable when we are looking for sets at a very high Jacquard similarity or low Jacquard distance. Roughly, these work well compared with the LSH techniques studied so far if the threshold for similarity is 80% or more. An advantage to these methods is that they are exact. There are no false negatives, although they still have false positives that need to be compared. The methods we discuss involve creating an index of sets, which is not too different from hashing sets to buckets. However, the indexes exploit a number of tricks. We sort the elements in each set and think of sets as strings. When we're looking for very high similarity, the length of these strings tells us a lot, since the similar sets cannot have strings whose lengths are too different. We shall also use tricks based on the prefixes and suffixes of the strings. To set the stage, we're back to talking about sets and their Jacquard distance. Recall that Jacquard distance is 1 minus the Jacquard similarity, and Jacquard similarity of two sets is the size of their intersection divided by the size of their union. Our first step is to represent sets by strings. The characters of the string are the elements of the set in order. That is, we pick an order for the elements of the universal set. For any set, we can sort its elements according to this order. The string representing a set is the list of these elements in the sorted order. The special property of these strings is that no character, that is, a set element, appears twice in the string. Let's consider the example of sets of K-shingles. That is, the universal set is the set of K-shingles, and the shingles being character strings can be ordered lexicographically so that there is the ordering of the universal set that we need. We have to make a little mental leap, however. At one level, shingles are themselves character strings, but we have to think of each shingle as a single character in a larger alphabet. We don't have a way to invent characters for each of these shingles, so we need to represent those characters with what look like strings of length k. So let's take a particular example. We'll use k equals 2, and the document we shingle will be ABCAD. The four shingles in this document are AB, BC, CA, and AD. Let's sort these shingles lexicographically. First is AB, then comes AD, finally BC, and then CA. The sorted list of shingles is thus AB, AD, BC, and CA. Again, understand that AB and similar strings are ways we are expressing single characters in this string of 4 characters. So this is really a single symbol, that's a symbol, that's a symbol, and that's a symbol. And we're representing strings as lists of these characters here to make the separation between characters clear. Let's see another example based on documents. We could represent a document by its set of words. This would be appropriate if we were looking for similarity based on topic rather than character by character similarity. Even though words are of different length, while shingles are all of the same length, we can still use lexicographic order, that is dictionary order, to sort the universal set of words. The fact that here the universal set is infinite doesn't matter because we can still tell the order of any 2 words, and that is all we need to sort the finite sets of words that come from documents. However, there is a better way to order words for the application we have in mind. Count the occurrences of the words in our collection of documents, and then order the words rarest word first. You can break ties lexicographically. The reason for putting the words with the lowest number of occurrences first is that when we index the strings that represent documents, we shall base the index on the first characters in these strings. The characters of these strings are actually words of the documents. So we are indexing documents in such a way that 2 documents will fall into the same bucket only if they have a very rare word in common. We want to have many buckets and very few strings in each bucket. Incidentally, we're talking about strings in a confusing way, so let's sort things out a bit. Documents are strings of characters, like this, ABC, blanks maybe. We bust the documents into words. The dog, we think of the documents as its set of words. So the set the dog, and we then create from these sets new strings whose characters are the words in order of fewest occurrences first. So we might have, for example, dog, the, and so on. I'm assuming that dog is a rarer word than the. It probably is. And it is these strings, or these objects, characters like dog and the, for which we'll create the indexes. Since we've converted sets into special kinds of strings, it is useful to start out understanding the relationship between the Jacquard distance of the sets and the edit distance of the strings. So suppose the Jacquard distance of two sets is J. These sets are represented by strings S1 and S2, and let the least common subsequence of these strings be of length C, and then let the edit distance between them be E. We claim that 1 minus J, that is the Jacquard similarity of the underlying sets, is C divided by C plus E. That is, the size of the intersection of the sets is C, and the size of the union is C plus E. To see why, notice string S1 has certain characters that S2 does not have, and vice versa. The only way to convert S1 into S2 is to delete the characters S1 has that S2 doesn't have, and then to insert the characters that S2 has but S1 doesn't. The union of the underlying sets is all the symbols in the LCS of S1 and S2, plus the symbols in S1 but not in S2, plus those in S2 but not in S1. Thus, the size of the union is C plus the edit distance. We should comment that this method of trying to convert S1 to S2 doesn't work in general, but it works here because the symbols they have in common appear only once, and they appear in the same order. Thus, the only LCS for S1 and S2 is their entire list of common symbols. And finally, we can reorganize the equation above that 1 minus J equals C over C plus E to get J, the Jacquard distance of sets, is E over C plus E. We're going to go through a series of progressively more complicated forms of indexes to put on the strings that represent the sets. Our first and simplest approach is to index by length of the string only. That corresponds to indexing sets by their size. There's an important relationship between Jacquard distance and lengths of the strings that represent sets. If a set has size L, so its string has length L, then this set can be Jacquard distance J from a set of size M only if M lies between L times 1 minus J and L divided by 1 minus J. We'll justify this relationship on the next slide. But for example, if J is 0.1, that is the Jacquard similarity 1 minus J of the underlying sets is at least 90%, then M must be in the range 0.9L and 1.11L. Or put another way, M must be at least 90% of L and L must be at least 90% of M. Here's why the relationship between L and M must hold. First, given L, how short could the other string be and still have Jacquard similarity at least 1 minus J? To maximize the Jacquard similarity, we have to assume that the set of size M is a subset of the set of size L. Then the intersection of the sets has size M and the union has size L. That is, the Jacquard similarity is M over L. And therefore, M is L times 1 minus j. Now consider the case where M is the size of the largest set that could be at Jacquard distance j from a set of size L. Here we must have the set of size L contained in the largest set. Their intersection has size L and the union has size M. That means the Jacquard similarity is L over M, and M is L divided by 1 minus j. If you don't know what B-trees are, it doesn't matter that much, but let me point out that B-trees are great for finding keys within a given range. So if we index strings using their length as the index key, we can find, given a length L, all strings whose lengths are in the range L times 1 minus j to L over 1 minus j, without having to look at any strings whose length is outside that range. That gives us candidate pairs of strings. However, just because two strings have similar length doesn't mean they have high Jacquard similarity. They could have completely different members. Thus, we need to compute the actual Jacquard similarity of every pair of strings of similar length. By the way, I have started talking about the Jacquard similarity of strings when what I really mean is the Jacquard similarity of the sets that the strings represent. I'm going to use that shorthand in the future, and I trust that there will be no confusion.